Now that we know how to identify if a carbon is chiral or achiral, we can now start to differentiate between enantiomers and diastereomers. Here, we're going to be looking at enantiomers first. An enantiomer, I swear these words just are going to get bigger, is a non-superimposable compound, like I had shown you with our chiral carbons, that is a mirror image. That means two compounds that are optical isomers. That means they have the same groups on their chiral carbons, and they are a mirror image. But we need to be able to differentiate between those two isomers. For our monosaccharides, we use the designation D or L in front of the monosaccharide name. The D and L are the direction of a hydroxyl group on a chiral carbon. Most specifically, the last chiral carbon. There's a baboon looking in the mirror. Before we bring in these large, awkward organic molecules, I want to provide just some simple imagery to really have this grasp of what a mirror image is, and therefore an enantiomer. So here we can see that the green cylinders are vertical, and we can also tell the way in which they are tilted is the same. And then we have the same groups. So imagine the groups are attached to the same carbon, or they're at the same point on this cylinder. It is a mirror image because the orange is essentially looking at itself, right? So if I had a mirror, I would see my nose. And this purple is also looking at itself, right? So it's like my chin would be looking at itself. That is what it means by mirror image. But it has to be every group on a chiral carbon. Has to be a mirror image. So here we're mimicking two chiral carbons. On each one, the groups placed are a mirror image. Again, think of it like the palm of your hands are facing each other and the back of your hands are away. So we always got some that are facing and some that are away. So when we overlap the two, they do not overlap precisely. This is what it's meant to be for superimposable. What if we flip that picture? When we flip that picture, that cylinder is now tilted in a different direction. Our groups are still in that mirror image form. However, when we overlap them, they still do not lap over, right? So it's not like you're clapping your hands. We are not rotating. We are placing on top, all right? So that what was facing each other in the mirror is now trying to be stacked. And that is what we are referring to by a non-superimposable mirror image. Now, when we get into our carbohydrates, we can have anywhere from 3 to 6 carbons in these structures. So we can have anywhere from 1 to 4 chiral carbons. Now, what makes these carbons chiral is how the groups are placed around the carbon we are looking at. We have to remember that these structures are actually three-dimensional and occupy that three-dimensional space. We get lazy and don't show the dimensionality for each of these groups like we should. Remember that the dashed represents a group going behind the picture, and the wedges are a group coming out towards that observer. In order to be that mirror image, our groups have to be going in the same direction. So this OH and H are both coming towards the observer, and the aldehyde and the alcohol are both going away from that observer. So when we look at our models, we can see that that carbon group is up above the other carbon. So that is why we have to use the dashes to show carbon 1 and 3 going behind carbon 2. And then we have the hydroxyl and the hydrogen on carbon 2 coming out towards the observer. That is what the molecule looks like in its three-dimensional space. Now, drawing these structures to show that three-dimensional space is not fun, so we're not going to. So a scientist who determined a way in which we can represent these chiral structures is to form a Fischer projection. A Fischer projection puts any chiral carbon at the crosshairs. It is not written in. Any A chiral carbon is written out in its condensed form. That is a very specific way to represent these structures so we know how they are occupying that three-dimensional space, but not having to draw it as such. Here we have glyceraldehyde as that three-carbon compound we had talked about in our metabolism, that this is the base compound that can make our three major macromolecules. Again, focusing on our carbohydrates. We have the aldehyde, so this is an aldose. There are three carbons, so this is also a triose, so glyceraldehyde is an aldotriose. The A chiral carbons can rotate freely, and it does not change the direction. They're still going behind. The terminal carbon, here carbon 3, can also rotate freely, and it still does not change position from going behind the carbon. It maintains that zigzag. If we were to rotate this second atom, it changes the positions of where the carbons are at. That is why the Fischer projection is very specific. Now within this Fischer projection, we have our two enantiomers of glyceraldehyde. What we want to look at then is the hydroxyl group on the last chiral carbon. There is only one chiral carbon in glyceraldehyde, so it makes it a little bit easier to start with. From there, we want to look at the hydroxyl group, because it's this hydroxyl group that gives these monosaccharides some of their properties. If the hydroxyl group is on the left side of that chiral carbon, that is going to be the L designation. So we would say that this is L glyceraldehyde. Which means that its mirror image isomer or enantiomer has to have the OH group on the opposite side of that same chiral carbon. The OH group is on the right side of that chiral carbon. The designation we use for this is D. Therefore, this is D glyceraldehyde. For our saccharides, D is naturally occurring, whereas we have to force or in lab make L. L is unnatural. So typically when we are working with our monosaccharides and starting to build up our polysaccharides, we're always working with our D enantiomer.